Thank you, Marcy, and thank you everyone for joining us. And as Marcy mentioned, we are going to be talking about DES 431, Demystifying Diaphragm Design. I'll be your first presenter, and partway through that, I'll give a little introduction and I'll hand it off to Buddy. He'll do an example and then he'll bring it back to me. So this presentation is copyrighted by American Wood Council, and it is registered with AIA for continuing education, as well as ICC and NCSEA. And Suzanne is providing you with a link to the PDF of the presentation, where we've incorporated the course description, as well as learning objectives that you saw when you registered for the webinar. So right off the bat, we'll start off with getting a feel for what the audience, or who is in the audience. And Marcy, let's come back and do this first poll.
Absolutely. So what is your profession? This one is the easy one. So tell us if you're an architect, engineer, code official, fire service, or builder, manufacturer, or other. We have 79% engineers, 13% code official, and just a little bit of everybody else, and we are just so happy that you are all here.
Great, and then we have one more poll to find out the experience of the audience.
Absolutely, and this one is a little fun, so use your imagination, and hopefully you all are fans of Marvel. So if you're to categorize your experience with design or plan review of structural wood construction, who would you be? So if you have limited exposure, would you be Groot, Rocket Raccoon, Black Widow, Captain America, or Iron Man? You could teach this course, so gauge your experience there in the middle. We have some good experience here in the middle, 33% Captain America, 29% Black Widow, 7% could teach this course, and 18% and 13% you are going to learn a lot. So happy to have you here.
Yes, thank you everyone for responding to the poll, and that gives us a good indication of the makeup of the audience. And we've got some material for just about everybody in the audience. We're going to start off with some basic information and get into 2 design examples and more. So just to give you an outline of how we're going to progress through the presentation, we'll start off with some basic information on lateral design, and then code acceptance of the standards with the wind and seismic provisions. And then I'll hand it off to Buddy, who will take it from there and cover a detailed design example using prescriptive diaphragm through design example through the wood frame construction manual. And then after that, he'll hand it back to me, and we'll really dive deep into the diaphragm deflection equation so that you can get some information to provide a really good foundation for what the equation is all about, some backgrounds behind the different terms in the equation. And then after that, once we gain that knowledge, we'll go ahead and do a design example to determine the deflection of the diaphragm, and then get into some information related to high load diaphragms. Now, we've included in the handout some FAQs that we've collected throughout the years from our information, our request for information desk or help desk in the FAQs, but we probably are not going to have enough time to get into covering each of those in this presentation. But we wanted to provide that to you because it has some very helpful information on commonly asked questions. And then last but not least, we'll get into some resources that'll help you beyond this webinar. So right off, we'll get into some basic information, general lateral load path. And as we know, as engineers and designers, or even construction people, we want to make sure we have a continuous load path through our building. Now, this is just a general look at how the loads are applied to the diaphragm, where we have the wind loads that blow on the windward walls, apply a pressure to those walls, and the stud span from the foundation to the diaphragm. The diaphragm acts like a beam and takes that load and transfers it to our vertical lateral resisting system, which is our shear walls. So that's the wind load path. And then if we're dealing with seismic loads, we idealize it and say that our mass is concentrated in the diaphragm, sort of like an inverted pendulum, and that load is mass times acceleration, and it's applied at the diaphragm, and that acts like a beam and transfers the load to our shear walls. Now, if we had a plan view of that, we would see a uniform load that is applied to this beam, which is a diaphragm, and the chords resist the bending of the loads, and then the diaphragm, which is the wood structural panel and the framing, resists the shear loads that are applied to the diaphragm. And those loads are resisted or transferred to the shear walls and resisted by the shear walls in each side. And then if we are resisting lateral loads of masonry and concrete structural walls, we additionally have to have continuous ties across that diaphragm. And that's in seismic design category C through F. And that's for ASCE 710 and ASCE 716. And it's not dependent, it's not just for wood diaphragms, it's for other diaphragms of different materials as well. But the bending is resisted by our flanges, which are top plates, and the shear is resisted by our diaphragm, or our wood structural panel and framing. And then when we look at this, we look at it as a beam, we can determine our shear and our flexure just from the basic equations that one would use for analyzing a beam. And we'll dive into that more deeper later into the presentation. Now, this presentation is based on the IBC, which is the 2015 and the 2018 IBC, which make it mandatory for when you're designing wood structures to use the wind and seismic provisions. That's the special design provisions for wind and seismic. Some people call it SPDWS. And then also to note is ASCE 710 and ASCE 716. Now, the 2015 IBC references the ASCE 710. The 2018 IBC references the ASCE 716. But the wind and seismic provisions, the 2015 references ASCE 710. So there's a little bit of off syncing of what's referencing as far as ASCE 716, but we want to make you aware that there is a difference between the codes and the standards. Now I'll go ahead and hand it off to Buddy, who will look in, get into the actual prescriptive diaphragm design.
All right, thank you, Michelle, and I'll also welcome everyone. For these examples, we're going to use a document that is available free on our website, a free download, called the 2018 Wood Frame Construction Manual Workbook. And in this workbook, we've designed a two-story residential structure for high wind, high seismic, and snow loads. And so you can easily download a copy of that. As I work through the presentation here, in the upper right-hand corner, you'll see a designation for each of the documents that I'll work from. The workbook is designated as shown here on your screen, and so I'm excerpting pages from that at the moment. And then I'll also be showing some pages from the 2018 Wood Frame Construction Manual and the 2018 Wood Frame Construction Manual commentary. And so up in the corner then of your handout, each one of those will be designated. Now, I've taken the page numbers out of this document so that we don't have confusion with page numbers for the handout. So we've had some comments about wanting to be able to know where I am in the wood frame construction manual or in the workbook, so I'll try and point that out along the way. This is figure 1 near the front of the workbook, and it just shows a nice metric view of the 2-story structure that we use for this example. So still in the workbook then, want to get a sense of the layout of the building. And so I'm going to scroll down here near the bottom of the page and just look at the top floor and the attic space and some of the other things about this example that'll be helpful. First thing to note is there is a finished attic over bedrooms 2 and 3. And so we've got a diaphragm there that's 25'6" by 32. We'll be looking at some designs for that. The dimensions for the main building are 32 by 40. And so our diaphragm sizes are going to be based on those dimensions. The diaphragm opening here in the middle is 10'8" by 12 feet. So that's going to come into play when we look at our diaphragm limits. Sorry about that. And then here over bedroom 1 is a vaulted ceiling where we have rafter ties. So we took the ceiling joists, we raised them up a third of the distance into the attic space, call those then rafter ties. And we're going to design that ceiling diaphragm to resist loads on the gable end wall as part of this exercise as well. So we'll design the roof diaphragm, floor diaphragm, attic floor diaphragm, and then this vaulted ceiling to give you a couple of different looks at diaphragm design. Down here at the bottom in these boxes are some other dimensions that are going to be necessary for the design. The wall heights are 9 feet, so that plays into the tributary area that's resisted. The roof pitch is 7 and 12. The mean roof height is 24.7, just a little under 25 feet. And then the top plate to ridge height, the very last value down here at the bottom, is 9.3 feet, so 9'4". So put a thumb, a dog ear on your handout, or just remember page 17 if you need to go back and look at some of these dimensions as we work through the examples. So what are the loads on this building? Again, as Michelle mentioned, we're going to be looking at ASCE 716 loads and 2018 IRC criteria. The wind speed that we're looking at here is 160 miles per hour, exposure category B. And so that's a pretty good wind speed that we'll be evaluating. We're also looking at just one example of a diaphragm with the seismic design. And so the seismic design subcategory in the IRC is D sub 1. So we're looking at seismic design category D sub 1 for this example as well. We show the gravity loads here. Those all come into play for seismic design. And so you'll see those showing up in some tables later on. I'm not going to spend a lot of time going through that, but one of the first things that we have to do before we even open up the wood frame construction manual is see if we're within the limits that are prescribed by the wood frame construction manual that allow its use. So here in this first column are the wood frame construction manual limits, and then our design case in the second to last column, and you see we're at less than 33 feet mean roof height, 3 stories. 3 stories is with that finished attic. And then our largest building dimension is 40 feet, which is under the 80-foot dimension that's shown as the max for the wood frame construction manual. The code references, sorry, we forgot to put those in at the beginning when Michelle showed the code references. But the 2018 wood frame construction manual is adopted by reference in the 2018 IRC. And so you see the reference sections there for alternative provisions and for wind design. It's also referenced in the 2018 IBC for calculation of wind loads and for the conventional construction requirements in the IBC. Now, section 2309 states that this is for risk category 1 and 2 buildings. So just be aware that it's a pretty limited scope where it can be used for non-res applications. And then there's a link there as well if you want a refresher on changes to the 2018 wood frame construction manual, which we'll be referencing here. And I think Suzanne will throw some of this information into that chat box if you want to copy that, or if you want to just jot it down on your PDF. But we can get that to you later if you missed any of that. Sorry, but that wasn't in your original handout. So what's next for the workbook? What you'll see in table W1.2, the prescriptive design limitations, are some additional look at what the limits are for the prescriptive provisions in the wood frame construction manual. That's chapter 3 of the wood frame construction manual. And so we're just going to be looking at floor and roof diaphragms today. So what this box, this red box on your screen around some of these floor diaphragm provisions does is it shows us what some of the limitations are for using the wood frame construction manual for this design example. One of those is a vertical floor offset limited to the depth of the floor joist. And so we don't have any vertical floor offsets in our particular example, so we're good to go there. I'm going to skip down here to the floor diaphragm opening limits. That's the lesser of 12 feet or 50% of the diaphragm dimension. Our largest opening is 12 feet for the floor diaphragm, and so we're good to go there as well. I'm going to just take a look then to see we don't have any openings in the roof diaphragm down there at the bottom of the page, so we're good to go there. Now, let's talk about aspect ratios and minimum and maximum diaphragm lengths. So in the wood frame construction manual, there's a table 316B for the minimum and maximum diaphragm lengths that can be used for wind design. And then table 316 has the max diaphragm length, which happens to be the same as the max building dimension of 80 feet for seismic design. So table 316B is for wind, table 316C is for seismic. We're going to look at both of those tables in just a second. And our maximum dimensions for our floor and roof are 40 feet, and for that attic floor is 25.5. So we're within the L min and L max that we'll be looking at here in a second in those tables. For the roof diaphragm, down here at the bottom of the page of your handout, page 20, table 316A is for wind, table 316C is for seismic, and you see the L min and L max taken from those tables as well. And our roof diaphragm dimension of 40 feet is within those limits as well. So those are lookup tables, and we show kind of the results here to show that, yeah, we can use the wood frame construction manual for this example. What we're trying to do with these diaphragm limits is keep us to a box structure, and that allows us to do primarily a strength-based design. We don't check deflection. We'll talk about that as we wrap up this segment of the event. This is also allowable stress design. So we don't use LRFD for this wood frame construction manual. It's all ASD. So we're going to convert all our wind loads to ASD. We convert all our diaphragm capacities to ASD. And you'll see that in the calculations that we run through. So we're going to switch over then to some excerpts from the wood frame construction manual, 2018 edition. Again, in the upper right-hand corner, you'll see the designation WFCM. And if you're following along in the wood frame construction manual, and I took your page numbers out, sorry, we're in table 316A1. So just scroll through till you find table 316A1. If you're following along in your wood frame construction manual, this is for the roof diaphragm for wind, and this is exposure B. It covers all roof slopes, and we'll just look right away at the 160 mile per hour column, because that's what our example is based on, is 160 miles per hour. Over here in the first column, then we're looking at the max top plate to ridge height. Ours is about 9.3 feet. So we're going to have to interpolate between 5 and 10 feet. Our roof diaphragm width in feet is 32. And so we'll interpolate between the values here and here. And down here at the bottom, then you see when we do that interpolation, we come up with that L min and L max of 12.7 and 70.6 that showed up in the table early on. You say, well, that looks like a black box. What's the background for all of these limits that you're putting in this table? All right, just stay tuned. I know you engineers in the audience are curious about that, so we'll get to that. But I want to show you two other numbers that I highlighted here. Under the 150 mile per hour column for a 24-foot building width and a 10-foot top plate to ridge height, I've highlighted these two values, 9 and 57. So the reason I highlight those is because when we look at the commentary here in a second, we do a solution in the commentary for a value or a set of values in each one of these tables in the wood frame construction manual. And so the solution that we have in the commentary is for this L min and L max that's shown here, 9 and 57. It's different from the example problem we're working. So I didn't want to create any confusion, because in a second when I show the commentary, we're going to do background calcs for these numbers, not for the numbers that we're using for our example. But what we want to show you is that this is not a black box. All the calculations show up in the commentary, so you can check those yourself to make sure that you're comfortable using the provisions that show up here. So that's our roof diaphragm, the floor diaphragm table. If you're following along in your wood frame construction manual, is table 316B. Floor diaphragm for wind loads, again, exposure B. And for the 160 mile per hour case, in this case, we're going to look at wall heights, because we're looking at tributary area of the wall above and below the floor diaphragm. And so our wall heights are 9 feet, and we're going to have to interpolate that. And so for that 32-foot floor diaphragm width, we come over here and we interpolate between these two values under the 160 mile per hour column, and we come up with the value shown here, which is 12.5 feet and 74 feet. So I'm going to show you in a second how we calculate or how we come up with those values. Next, we want to look at the seismic table. Again, we're in the wood frame construction manual, table 316C1, and this is for seismic, and this is for a ground snow load of 30 pounds per square foot. You see all your gravity load assumptions here at the top, and so all those gravity loads are summed up to create that floor or that either floor or roof diaphragm weight. And Michelle mentioned the inverted pendulum. We use that to calculate the floor weight that then we use to calculate the seismic load on the shear walls and the diaphragm. And so our seismic design category is D sub 1. And for a roof ceiling diaphragm of 32 feet, we work across and we see that the max diaphragm dimension is 80 feet. That corresponds to our max limits in the wood frame construction manual. And notice this diaphragm load ratio, 0.54. That just shows our actual loads to allowable load or allowable capacity of that diaphragm. For the floor, very similar approach with a 32-foot width, an 80-foot max diaphragm dimension, and a 55% load ratio. That's basically means we've used up 55% of the capacity of that diaphragm. All right, so it's not a black box. If you have the commentary and you're following along, we're looking at the commentary for table 316A1, which is the roof diaphragm limits for wind. And what I'll walk through here is how we come up with those L-min and L-max values that we showed in the table. And so we're going to look at those minimum, maximum based on the diaphragm capacity. The diaphragm capacity is obviously based on the sheathing thickness, nail size, panel edge nailing, and supported panel edges. I mentioned the values that we're looking at in that table are based on these parameters, different from the specific example that we're looking at, but this gives you an idea of how we solve for the values in the table of the wood frame construction manual. For the minimum aspect ratio, it's going to be a 1:3 limit on the diaphragm. For the maximum diaphragm aspect ratio, it's 3:1. So that's the one of the limiting factors is that 3:1 diaphragm aspect ratio. So to determine the minimum roof diaphragm length, we're going to look at two controlling factors. And we're going to look at the wind load acting parallel to the ridge of the roof. If we go to chapter 2 of the wood frame construction manual, table 2.5b, we tabulate those roof loads parallel to ridge, assuming a top plate to ridge height of 10 feet. And so for this particular value in the table, we have a load on that roof diaphragm parallel to ridge of 155 pounds per linear foot. So we can do the math then based on the diaphragm width and come up with the load into the top of the shear wall of 1,860 pounds. So that's our load. And we go to the wood frame construction manual table. Then we go to the wind and seismic standard, the 2015 wind and seismic standard, table 4.2c, and come up with a nominal unit shear capacity of 450 pounds per linear foot. We divide that by 2 for allowable stress design. We come up with an allowable of 425 PLF. That's greater than the actual load. So if we just wanted to know that our diaphragm capacity exceeded the load, then we could stop there. We want to figure out those minimum roof diaphragm lengths though. So we're going to do the math here to divide the load by the capacity to come up with that 9-foot minimum length. Our aspect ratio limit is 3:1. So that would actually give us an 8-foot minimum length, but we're going to use the one that controls, which is 9 feet. So that's how we come up with that minimum roof diaphragm length. It's the greater of the two shown here in this calculation. I know I'm moving fast, but we got a lot to cover. So next is the maximum roof diaphragm length. That's going to be based on 3 limiting parameters here, and we're going to look at wind load perpendicular to the ridge for this analysis. One of the things about the wood frame construction manual that I hope you can appreciate is all the ASCE 7 wind load calculations that we've done. Here are the average pressures on the walls, on the roof. Oh, sorry, let's see. This is average pressure on the wall for a 12 and 12 roof pitch, and then average pressure on the roof for a 12 and 12 roof pitch. And again, this is perpendicular to the wall, and you can see the calculations there. And then back up at the top of the second column here, then we're going to use those wind pressures to calculate the roof diaphragm load of 249 pounds per linear foot. So that's our roof load, or roof diaphragm load. Then we're going to go to the wind and seismic standard, table 4.2c. In this case, we come up with a capacity of 300 PLF for the allowable stress design capacity. This is based on a 3/8 inch nominal panel thickness with 2-inch framing and case 1 sheathing direction. So that case 1 sheathing direction is a strong axis. That's why we've got a higher capacity here in that strong axis versus what we calculated previously parallel to ridge was case 3, which was the weak axis for that sheathing. So that's our sheathing, roof sheathing capacity. So we'll take that to calculate the maximum sidewall length of 57 feet based on capacity. Then we've still got that 80-foot limit for the wood frame construction manual overall cap of 80 feet. And then we've got our aspect ratio limit of 3:1, which is 72 feet. So we're going to take the smaller of these three as the controlling factor. So in this case, capacity actually controls the maximum diaphragm length for that roof diaphragm. Now that's a fairly minimum sheathing. 3/8 inch on a roof is probably not that all that common. It's probably gonna be 7/16. So you probably have a lot higher capacity in a lot of cases, but we've given a pretty conservative approach for these tables in the wood frame construction manual. So you know what they're based on. Floor diaphragms are going to be very, very similar. So we're not going to spend a lot of time going through the floor diaphragm capacity. Other than I'll point out here under background for table 316B in the wood frame construction manual commentary, that the floor sheathing that we assume here is about a 1/2 inch, 15-30 seconds, 1/2 inch sheathing. Again, pretty conservative for floor sheathing. You likely will have a thicker sheathing, but that allows you to calculate the minimum capacity from the 2015 SPDWS table 4.2C, and then compare that to that aspect ratio limit of 3:1, which gives us 12 feet. So the 14 feet is what actually controls for the minimum floor diaphragm length. Maximum diaphragm length then ends up being 80 feet if you run through the numbers and compare the three options. So again, very, very similar to the roof diaphragm. Not going to spend a lot of time on the details there. Next page, though, gets us to the seismic background information. This is table 316C1 in the wood frame construction manual commentary. And this again is for the seismic table. So the background here is a little bit different because the seismic load is going to be the same parallel and perpendicular to the roof. So we don't have to look at two different sets of tables for this. We still are going to have that 3:1 aspect ratio limit and an 80-foot max roof limit. For this particular roof ceiling diaphragm, we're going to assume 3/8 inch wood structural panel sheathing. If we go to the tables, we come up with a capacity very similar to what we came up with earlier for the roof diaphragm. We work through then the seismic provisions from ASCE 16 to come up with the load on that roof diaphragm. It ends up being, for this 2-story structure, 67 pounds per linear foot. That's less than the 215 pounds of capacity. So we're good. We're going to tabulate that maximum of 80 feet. And then we show one more thing in that seismic table, which was that diaphragm load ratio. And that's simply taking the load, the actual calculated load, divided by the capacity of the diaphragm. The floor has similar calculations except for a thicker sheathing, which is common for floors, to come up with those max limits for the floor diaphragm. So that's a very quick background on how we develop the tables, the diaphragm tables for the wood frame construction manual. If you are a code official, that helps you do some quick plan check review on things that may be coming across your desk for high wind, high seismic applications. If you are an engineer and you're doing residential design, we know the margins are pretty tight for residential design, and so hopefully there's some tools here that you'd feel comfortable with that will help you if you're analyzing residential structures for high wind or high seismic applications. And so we're going to switch gears now and look at the attic floor diaphragm and the ceiling diaphragm in the in that bedroom where we've got that vaulted ceiling. And so for those of you using the again using the workbook, we're in figure W4.1 in the workbook. And note up here in the top right hand corner the little icon that shows you where we're reviewing or what we're designing in the structure. In this case, we're in that finished attic space in that top right portion of the icon there. And this is that finished attic space. And there you see the cross-section plans for those and plan views for those parts of the structure. Again, in the workbook in the top right, when we switch over to that vaulted ceiling, then you see the plan view changes here, and we've got that ceiling joist that's 1/3 of the way up into the attic space. And so when we look at this ceiling diaphragm here, we've got some additional tributary area in the wall that we'll be looking at. And notice also that we don't have a windward and leeward wind load on these diaphragms. We're going to have just either a windward or leeward load, whichever is the worst case, but we won't be doubling up on a windward and leeward load for these two different diaphragms. So we'll talk about that and some of the adjustment factors you can use to help out in that process as well. Reminder that this diaphragm for the roof ceiling diaphragm is going to be smaller because it's further up into the that rafter, that attic space. So it's a 21 by 14'6" diaphragm. So let's look at the floor diaphragm and the finished attic first. That's going to be a typical floor with 2x10, 16 inch on center, #2 joists, and 19/32 wood structural panel sheathing. One of the things you'll see in the wood frame construction manual that we'll look at here in just a second is section 3.3.5, which says that it's a prescriptive statement that says if your wind speed is greater than 130 miles per hour, and we're at 160, that you need to put blocking in the first 2 bays of that floor diaphragm at 4 feet on center to stiffen up that diaphragm. So we're not going to do a full block diaphragm, but we are going to put some diaphragm blocking in to stiffen it up to help transfer those loads from the end wall into that floor diaphragm. Then when we get to the roof diaphragm, we've got a similar provision that's in WFCM 3.5.5 that says you're also going to block in those first 2 bays at 4 feet on center. However, there's an exception that says if the attic floor is used to brace the gable end wall, then you don't need that roof diaphragm blocking. And so we're going to put that blocking in the attic floor diaphragm, so we don't need to block the roof diaphragm at that end. So that'll save us some additional blocking in the design. And we're back to the wood frame construction manual here just to show you chapter and verse, section 3.3.5 that I just alluded to. And then the next page is the wood frame construction manual, section 3.5.5, and that exception about the attic floor that gives us a way out of that roof diaphragm bracing. So I'm going to jump back one page, page 36 of your handout, and I want to look at wood frame construction manual, section 34112. Sorry, I'm trying to get that highlighted here. And what that says is that when the attic floor or ceiling diaphragm is used to brace the gable end wall, then we're going to look at table 315. So to design the diaphragm over top of that vaulted ceiling, I'm going to be looking at table 315. So now, again, we're back in the workbook. We are in the vaulted ceiling area over that first bedroom. We could, if we want, we could balloon frame the studs and block the rafters at 4 feet on center, and use those rafter, that roof diaphragm to carry all the load from those studs, those balloon framed studs. But we'd end up with studs, probably 2x6 number 1 or select structural studs to span that 18-foot distance to the peak. So that's probably not a very practical approach. So what we'll do is we'll look at table 315 and see if we can use the the ceiling diaphragm gypsum down here in this detail at the bottom. Can we get gypsum in that ceiling diaphragm to brace that gable end wall? Now remember that ceiling diaphragm is raised up into the attic space, so the diaphragm width or span is 21 feet. The other issue that we're going to see in a second is that if we want continuity there at that diaphragm, we're going to have to frame the studs up to that diaphragm 13 feet from the floor, the second floor. So we're going to have 13-foot studs, which means we're going to pick up some extra tributary area of those studs. They're no longer 10-foot studs that we assume in the rest of the building. So we're going to run through the gypsum calcs first, and then we'll run through the wood structural panel calcs in table 315. I'll just go ahead and give you the bottom line here. When we run through the calcs for gypsum, we're not going to have enough. That's what this NG is here. It's only going to give us 16 feet. We need, I'm sorry. Yeah, it's going to require 16 feet of gypsum. We only have 14.5 feet in that room to draw from. So it's not enough gypsum diaphragm length to give us what we need. So we're going to end up with wood structural panels instead. It's only going to require 8 feet, about 7.8 feet. And we've got 14.5. So I'll get to those calcs in just a second, but the other thing I want to point out in this diagram before we move to the next page is making sure that we can transfer those end wall loads at this hinge point. So where the stud wall frames into the gable end framing or gable end truss, we've got a hinge that can form. So we could have either windward loads that put this in compression. We can have leeward loads that put this wall in tension. So these rat runs, these 2x4s on the top of the ceiling joists are going to handle the compression load if it's a windward load. These straps on the end are going to handle the leeward suction loads and make sure that we don't blow out that wall with suction load. So there's some additional detailing there just to take care of this hinge that can form at that gable end wall and make sure we get the load into the diaphragm. All right, so wood frame construction manual, table 315B, minimum attic floor ceiling length when bracing the gable end wall. So we're exposure B, 160 miles per hour. And what I want to do first is show you the gypsum down here at the bottom of the table. So let's scroll down to the bottom, gypsum, and we've got a 7 and 12 roof pitch. Our diaphragm width is 21 feet, as we mentioned before. And so you interpolate that, we end up with about 18 feet. We're going to see that we got to take some adjustment factors here that are going to knock that down to about 16 feet. And so that won't work. Up here at the top of the table then, you see we've got the wood structural panel section for 7 and 12 and a 21-foot diaphragm dimension. And that's going to interpolate to about 8 feet, 7 point something feet. And with the adjustment factors for that, that will end up working out for us because it's only going to require 8 feet of diaphragm length, and we've got 14.5 feet. So the footnotes are what kind of throw this off. Footnote 1 for this table, 315, says that we're going to assume a gable end to gable end assumption, which means a windward and a leeward load on that ceiling diaphragm. Well, we don't have that. We're designing this diaphragm just from one end. We've got the attic floor on the other end. So in this case, we can actually reduce that diaphragm requirement by a certain percentage because we've only got load from one end of the building. The other thing that kind of throws a pretty big load onto our diaphragm is this wall height assumption. We assume a 10-foot wall height. We've got a 13-foot wall height there at that raised ceiling. And so we've got to account for that with this factor of h plus 1 over 10. So that actually bumps us up pretty considerably. The other bump we get with our gypsum, but it's not enough, is that if our framing's at 16 inches on center, then we can take an additional capacity adjustment, a bump on that gypsum, and I'll show you where that comes from here in a second. So I'm just going to jump back up to the workbook, a couple of previous pages here at the bottom of page 38, just to show you how through all those factors in there. We've got the tabulated value, 18. We've got this 0.84 adjustment for the bracing only one end versus a windward and a leeward load. This is the one that kills us at 30% increase for the wall, that 13-foot wall below. So we're picking up that tributary area of that 13-foot wall below. And so doesn't give us quite what we need for the gypsum. We end up going with a wood structural panel that could probably go on either side of these ceiling joists. You could put it on the top side or the bottom side, put it on the bottom side and then put the gypsum over top of it. Depends on whatever your framer's preference is for doing that to get that diaphragm to work. All right, I don't have time to get to the background calcs for that table. So this is a wood frame construction manual commentary. You can look at this on your own. Table 315 commentary shows all the capacities, all the loads. The one table I will point out to you though is this wood frame construction manual supplement table S3, which gives us our gypsum capacity. So if you're looking for where we came up with that gypsum capacity, jump down to that table here real quick. This is the table where we get our wind loads from table 2.5C of the wood frame construction manual. Again, if you want to use the wood frame construction manual just to calculate your loads and do your own design, that's great. That all those loads are tabulated for you in chapter 2. Here's our table in the wood frame construction manual, table S3, that gives our ASD, unit shear capacity, for horizontal gypsum wallboard diaphragm. 70 PLF allows you to bump that up to 90 when your framing's at 16 inches on center. Michelle will talk about the tables from the Wind and Seismic standard, and again, all of those capacities are what we use in the 2018 wood frame construction manual. So I won't spend any more time there on that. So we'll get to this next polling question, and Marcy what do you got for us?
Alrighty, so the maximum roof and floor diaphragm lengths in the WFCM tables 3.16 A and B are based on is that the diaphragm capacity, maximum prescriptive building dimension, aspect ratio limits, all of the above, or answers B and C. All right, so 66% say D, all of the above, and 28% say answers B and C. So tell us what the real answer is, buddy.
All right, so the answer is D, all of the above, and I covered this a while back, but the maximum prescriptive building dimension of 80 feet is also going to be a limit that means that all of these apply. So the answer is all of the above, and I'll turn it over to Michelle, and she'll take it from here. And while we're making that transition, let me just share, some of you may be asking about deflection calcs. So I mentioned that we're just using the wood frame construction manual based on a strength approach, a capacity approach. It's allowable stress design, but it's we're not looking at deflection calcs. And the reason we don't do that is twofold. One, for most wind design application, deflection or drift limits aren't required. For residential applications, it's not required for either wind or seismic. And so if you're in an application where drift limits are required and you have to calculate shear wall or diaphragm deflections, Michelle's going to pick up here and take us through diaphragm deflection calcs using the 2015 Wind and Seismic standard. Take it away, Michelle.
Okay, thank you, Buddy, and thank you everyone for sticking around. As Buddy mentioned, I'm going to be going over diaphragm deflection as it relates to the wind and seismic provisions. And right now we'll look at the actual diaphragm deflection equation. Now in the IBC, we see that they have a 4-part equation, which only applies to staple fasteners and wood structural panels, and they are of block diaphragm, or it's a block diaphragm. In the wind and seismic provisions, we provide some more methods of determining deflections to take other types of diaphragms into consideration. And so unlike the IBC, which has that 4-term deflection equation for wood structural panels and staple fasteners, the wind and seismic provisions has a 3-term deflection equation, which can be used for nail fasteners. And it's an algebraic simplification of the 4-term equation that you see in the IBC, which is shown here. This equation can be used for flat and folded diaphragms and can be easily calculated now that it's a 3-term equation using the provisions and the tables within the wind and seismic table, wind and seismic provisions, with a variety of sheathing materials, and also extends it to unblocked diaphragms. Now, I mentioned the 4-term equation, which you see here. We still include the 4-term equation, but that's in the commentary. And just to go over what the 4-term equation includes, it includes the bending chord deformation excluding slip in this first term. And then the last term looks at the bending chord slip, splice slip. And then the middle term looks at the shear panel deformation, and then the shear nail slip. And if one were to look at the two equations, the 3-term versus the 4-term, and plot it on a graph, we have on the horizontal axis the displacement and the vertical axis the load. The 3-term equation, which is a linear 3-term equation, is this solid line right here. Then the nonlinear term equation, or the 4-term equation, is this dashed curve line that's been plotted out. Now you notice there is a difference between the two equations. However, when we're looking at strength level forces, which is at this 1.4 times allowable stress design, the two equations are identical. That's an important thing to consider. And I did mention that the 3-term and the 4-term provided for this particular plot 2 different results between that, and it's only a maximum difference of about 0.045 inches, which is very insignificant when you think about it. That's less than a 1/16 of an inch. But the other thing that I want to mention is that for the linear term, the 3-term equation, we introduce a term that is the apparent shear stiffness. That's the G sub A. Now, the G sub A is based on the capacity, the unit shear capacity of the diaphragm, rather than the induced load on the diaphragm. So that's why when we look at the graph, we would have more displacement for the 3-term equation because it's based on the capacity rather than the induced. The induced obviously would have less deflection or displacement. So that's one big difference. Although the actual mathematical displacement difference is very insignificant. Now, in the commentary, I mentioned there is the 4-term equation. We've also included in the commentary the 3-term equation, just for ease of referencing. It's repeated there. The 3-term equation has the same equation for the first and third term as you would see for the 4-term equation. It's where we have a mathematical derivation here for the middle term to make it easier to use and to incorporate the apparent shear stiffness. Now, looking at the first term, we see 5/8 times V L cubed over EAW. V is the induced unit shear of the diaphragm. L is the length, and EA represents the properties of the chords. That would be, in our case, we're going to assume that the top plates of the diaphragm act as our chords. And E is the modulus of elasticity of the diaphragm chord, and A is the area of the chord, cross-sectional area. And the W is simply the diaphragm width. Now, the 5/8, just so you're aware, is that the 5/8 constant incorporates background derivations that cancel out the units of feet in the first term of the equation. So you want to make sure that you're using the proper units for each of these variables, the V, L, E, A, and W. So it's important to consider that and look at what the units are in the wind and seismic provisions. And the last term, again, incorporates the chord splice slip. And this equation is a summation of the splice slip. So it's a summation of X times delta C. X is the distance of the chord splice to the nearest support. And the delta C is the diaphragm chord splice slip at the induced unit shear of the diaphragm. Well, we'll get more into this later on in the presentation to get more detailed. So now let's look at the shear panel deformation and nail slip, that middle term of the 3-part equation and the 4-part equation. As I mentioned, that this 4-term equation, the middle term includes information or calculation including shear stiffness of the panel and then the deformation of the nails. And stepping back a little bit, the distribution of shear forces amongst the shear panels in a diaphragm is a function of the layup of the nailing patterns of the panels to the framing. And then for this reason, the shear deflection in a wood diaphragm is related to panel shear, panel layout, nailing pattern, and nail load slip relationship. And so in the 3-term equation, panel shear and nail slip are assumed to be interrelated and have been combined into that single term to account for shear deformations. Now we look at the apparent shear stiffness, G sub A, and how we calculate the G sub A. So the G sub A takes into account the shear stiffness that you saw in the 4-term equation and also takes into account nail slip which is the E sub n. But notice what I mentioned earlier is that the shear that's used for calculating apparent shear stiffness is based on the unit shear capacity, not the induced shear. And then we multiply it times 1.4 to convert it from an allowable stress level design to a strength level force. And that's required by ASCE 7 when designing for seismic design, seismic story drift. So where do we get our information if we are doing our four-term deflection? Where there are tables in the commentary that provide us with information for shear stiffness, that's the G sub V and T sub V for OSB and plywood. That's given in this actual table. And then for wood structural panels. And then we have another table that incorporates other sheathing materials, such as plywood siding. Now that would be for shear walls, particle board, structural fiber board, gypsum board, and lumber. So we've included additional information for more tools for developing or determining the deflection of the diaphragms for other materials than wood structural panels. And then we have other term for the four-term deflection is the fastener nail slip, and that's E sub n. And that fastener nail slip can be determined using this table in the commentary of C4.2.2D. Now, we often get a question of when we're determining the fastener nail slip, what nailing spacing do you use to calculate E sub n? And that is, do we use the boundary nail edge nailing or do we use the interior panel edge nailing? Well, what we found is, doing some calculations is that using the interior panel edge nail spacing in lieu of the boundary nailing provides a better result and reflects more reasonably well with what was shown in the testing data. And that testing data is summarized in a table, which is table C4.4.2E. So if you're interested, that's in the commentary. If you wanted to crunch your own numbers and find out what you come up with using the interior panel edge nailing, it should be close to what is tested. And so one would go to the table in this example, you would go to table 4.2A for blockwood structural panel diaphragms, and you would use the panel edge spacing, nail spacing to determine your fastener slip rather than the boundary nailing. So we also have tables that we have to easily come up with the apparent shear stiffness if we're doing the three-term deflection. And that's what's so great. It cuts out all those other equations where you can come up with just one equation rather than those two other equations to come up with that middle term to reflect the shear resistance. And we have here the nominal unit shear capacity, and we have the apparent shear stiffness for OSB and plywood. And this is for blocked wood structural panel diaphragms. And then we also have it for high load diaphragms where we're having multiple rows of nails and also 3x or 4x nominal framing members. We also have it for unblocked diaphragms with various load cases and providing the nominal shear capacity as well as the apparent shear stiffness. Now, all of these tables make the assumption that the moisture content of the framing is less than or equal to 19% moisture content. Additionally, if you have, it assumes 3-ply also for the wood structural panel. And if you have something like 4-ply or 5-ply or particle or something other than the 3-ply, you are allowed to increase your apparent shear stiffness by 20%. Okay. And then in addition to that, there are values, nominal shear capacities for lumber diaphragms, as well as the apparent shear stiffness shown in this table. Now we have a polling question coming up, and this is slightly different than the one in your handout because we noticed an error there. So go ahead, Marcy.
Alrighty, so the special design for provisions for wind and seismic has tabulated shear stiffness for which of the following products? Is that the wood structural panel, lumber, gypsum board, or all of the above? All right, so 80% say all of the above. I sure hope that that is the answer.
All right. Okay. Yes, it is all of the above. Good. A lot of people are listening. We have shear stiffness for, that's G sub V, T sub V, shear stiffness values, tabulated shear stiffness values for wood structural panel, lumber, and gypsum board. Okay, now we're going to get into a step-by-step design example to dive in a little even more deeper to get some explanation on the actual equation. So this example is actually in our commentary in the 2015 Wind and Seismic provisions, and it's example C4.2.2-3. We have a rectangular diaphragm that has a length of 48 feet, a depth of 24 feet. And the layout of the wood structural panel diaphragm, which is an OSB sheathing of 7/16, is case number 1, which is also blocked diaphragm. We're going to assume that we have 8 penny common nails at 6 inches on center at all panel edges. And our applied load, it happens to be our capacity of the diaphragm. So in this case, we're assuming that the capacity of the diaphragm is going to be our applied load to the diaphragm. Now, as engineers or designers of diaphragms, you will most likely use your actual induced load on the diaphragm rather than the allowable diaphragm load capacity, but in this case, again, we're going to use the 255 pounds per linear foot. So we are going to calculate the mid-span deflection for the blocked wood structural panel diaphragm, and then we're also going to design the cord splice. Now the difference is for the diaphragm cord splice, it's going to be sized using the allowable stress design loads. However, the deflection of the diaphragm, we're going to be using, because we're designing for seismic, it's going to be based on a strength design load, and that's in accordance with ASCE 7. And what's shown here is where we go to our wind and seismic provisions in the tables to get our diaphragm apparent shear stiffness, we get our allowable unit shear capacity, and then our cords are, it's a given because we have 2x6 walls, which is a part of the given in the problem, is we have two 2x6, number 2, Douglas fir large. Our modulus of elasticity is going to be 1.6 to the 1.6 to the 6th power for pounds per square inch for modulus of elasticity, and our specific gravity for the Douglas fir large is 0.5. Now, right off the bat, as I mentioned in the previous slide, we go to table 4.2.4, and this is where, this is a truncated look at the table where we're only showing the seismic of columns for the spacing of the nailing at 6 and 6. And we have our apparent shear stiffness of OSB of 14, so which is shown here. And then we're doing our nominal unit shear capacities of 510 pounds per linear foot. Now remember, this table is based on dual format so that we can do both an ASD design and an LRFD design. So we have the nominal unit shear capacity, and to get it into an ASD design, we divide by 2. And then once we have all that information, now we determine what is the demand on our wood diaphragm. So we have that uniform load of 250 pounds per linear foot. We treat it as if it is a beam. And we have our shear, which is simply the W times L divided by 2. We're assuming a flexible diaphragm, so half the load goes to this wall and half the load goes to this wall, and they divide by 24 to get it into a pounds per linear foot. And then we determine what our moment is. Similarly, it's based on the beam equations of WL squared over 8 for our maximum moment here, right here. And then for this example, we're going to assume that our cord splice is at 16 feet away from the support, and this is 16 feet as well. So this is where we'll design the actual cord joint. And we can determine that moment based on this equation, WX time L minus X over 2 is what our equation is. So we come up with 65,280 foot-pounds for our moment at that location. Now, utilizing that, all that, the first part of the design is we're going to design our cord splice. With a given of 2x6, number 2 Douglas fir larch, we have all that given information. And we're going to say that for each cord, one top plate is designed to resist the induced axial force, whether it be tension or compression. And then the second top plate is designed as a splice plate, which is shown here. We have, this is the cord, and we're going to have the splice here and the splice here. And then the connection, we're going to use 16 penny common nails. So going to the NDS, table 12N, we can find out what our capacity is for a 16 penny nail, which is 141 pounds. And then we multiply times the load duration factor of 1.6 for seismic loads, and we get 226 pounds. That's for one nail. Now, what is our cord force, the axial force, either tension or compression? Well, we take our moment, which was 65,280, and we divide by the depth of the diaphragm to get that axial force, which happens to be 2,720. And to determine the number of nails, we divide that by our capacity of our nails, and we come up with 12 nails. Now, that's assuming, again, that the splice is at that 16-foot location. But if you're in actuality out in the field, we don't really know where that splice is going to occur. So we may want to design all the splices based on that maximum moment, which is 73,440. And so when we do the math, we see that it's only 14 nails. And so in the whole scheme of things, that adds 2 more nails, which is not, it doesn't add a whole lot of cost to the overall scheme or the overall cost of the actual project. So it would, an engineer would probably do it per the maximum moment. But for, again, back to the design though of this example, we're going to take it at that 16 foot. So now to determine the deflection at the midspan, we are going to use the 3-term equation, which is shown here. And this is the second part of the design example. So for the first term, we're now, instead of doing an allowable stress design as we did for the cords, we're going to do a strength level design, which is required by ASCE 7. And we plug in the numbers here. And so we have 5, which is part of the equation. And then we have the actual induced shear, which is equal to the allowable shear of the diaphragm. And we multiply it times 1.4 to get it up to that strength level design. We have the length of the diaphragm at 48 feet, and we divide by 8. And then we have the actual EA, and that is of that single chord. So the E is the 1.6 of the 2x6 chord, and then we have A, which is the 8.25 of one of the chords, and the W is just the is just the 24 feet. So you plug that all into the equation and we get 0.078 inches. That's the deflection for that first term, which takes into account the bending chord deformation, excluding any slip at the splice. And as I mentioned, we are taking into account only one top plate in the design. If you were to take both top plates into the design, it would yield a 0.04 inch, which is less than what you see for just including one top plate. So then we get into that middle term, which takes into account the shear, and it takes into account panel shear and nail slip. This is the equation here, 0.25 times VL over 1,000 over the apparent shear stiffness. And the apparent shear stiffness is easily provided from the table that we had at the beginning of the example. And plugging that all into the equation, which makes it very easy. And again, we're using 1.4 times 55 pounds per linear foot. We see that the shear, panel shear and nail slip taken is 0.306 inches added to our deflection of our diaphragm. And then the last term, the third term in that three-part equation, now this is where we're doing the bending portion and looking at the chord splice slip. And that's the summation here of all the deformations that are occurring at the splice. So as you recall, we said that the splice was at 16 feet, and that's our X. And then we need to determine what our delta C is. And we said what the X is. And our delta C is that joint deformation due to the chord splice slip. And to determine that, we have the equation of 2 times T or C, depending on what we're looking at. If we're looking at the tension splice or the compression where the two chords come together and there are movement at those two chords in compression. And then we have it over gamma over N. And that's there. And looking at that equation. Now, we'll get more into that equation, but I want to explain the chord force, which is the T tension or compression. We determined what that was when we designed our chord force, our chord splice. But in this case, we've got to multiply it times 1.4 because, again, we're looking at strength level forces, and that's what we do here. Instead of being, what was it, 2,700 something, we are now at 3,808 pounds for that force. And when we look at the gamma, it reflects the load slip modulus of the actual dowel type fastener, we would turn to the NDS. And there's an equation in section 10.3.6 that provides an equation shown here of 180,000 times the diameter of the fastener to the 1/5 power. So to get the diameter of the fastener, we go to table L4, and that provides a lot of various fasteners. We happen to be using 16 penny nails, and the diameter is 0.162. We plug that into the equation, which is shown here, and results in 11,737 pound-inch per nail. And that provides us with our load slip modulus for that dowel. Going back to the equation for determining the deformation at the nail or the chord splice, we get delta C equals 2 times the T or the C, whatever we're looking at, and the gamma over N. So we plug that over the strength level chord force, plug that into the equation, divide that by the load slip modulus for the fastener, and then we have 12 nails. Remember, we're looking at the cord splice at the 16 foot. If we were looking at the midspan, where we went up to 14 nails, we'd use 14 nails. So that equals 0.054. Now we use this 2, which is a constant, because we need to account for that slip on either side of that joint. Remember, we have 2 sets of nails on either side of that joint to transfer that load across the actual cord splice. So for the tension cord slip calculation, we sum up that we have 2 cord splices, and we sum that up by doing 16 feet. That's the distance to the actual location, and multiply that times that delta C. And then we divide by 2 and 24. And then that's just for the tension. We also have to consider compression. And what we assume is that the compression cord butt joint has a gap. We're assuming that it has a gap that exceeds the splice slip. And so we equate that to similar to the tension cord slip. And that's why we say that the compression cord equals the same as we have for the tension cord. And literally we're multiplying times 2 to come out with the total deflection for that cord splice slip, which is 0.072. So if we look at each part of the equation that we just calculated, and here the first term in your handout, there was a typo there. It should be 0.078 rather than 0.78. But looking at for the first and last term, that takes into account the bending. First one is bending due to, and then the cord deformation excluding slip, and the last term is the cord splice slip. You can see that those 2 terms really don't add a lot to the actual overall deflection of the diaphragm, whereas the shear that takes into account the panel shear and the nail slip, that adds quite a bit, the majority of the deflection to this overall deflection of the diaphragm. So something to consider when you're trying to tighten up the deflection of your diaphragm, where you would have more impact is where you would have take into account the shear panel, the panel shear, and the nail slip of your diaphragm. So tightening up your nail spacing or the apparent shear stiffness of the actual diaphragm to really getting a lesser deflection. So now we're going to look at high load diaphragms, and we'll go through this quickly as we want to save some room for questions. But the high load diaphragm, this is an example of a high load diaphragm where we're dealing with big warehouses. This one it happens to be in Ontario, California, where they store a lot of produce or products. And this is a GE warehouse storage facility. They are, this one's over 1 million square foot facility. And this is where high load diaphragms can come into really helpful for providing a wood solution to that diaphragm. For those that are not familiar with panelized roof systems or pre-assembled roof systems, what you see here is an example of one method of doing it, where we have the framers on the ground that are assembling these. You see the sub-purlins here, 2x4s or 2x6s that are set into place. And then we have the steel bar joists here that support this pre-assembled assembly. That's constructed off-site, on-site, on the ground, which is a very safe way of constructing it. And then it's lifted into place. And then you have 2 framers on the roof that are tethered off for safety. And one is there to weld the bar joist to the girder. And then the other framer as they're nailing off the diaphragm to that common framing member. So they can really construct these real fast, and that's one advantage of having these panelized roof systems. And the advantage of using high-load diaphragms is you have a much higher capacity for these high-load diaphragms. However, it does use multiple lines of fasteners, 2 to 3 lines of fasteners, and the minimum width of the framing members is 3 by or 4 by. And for these type of framing or diaphragms, it does require special inspection, specifically under 1705.5.1 that has special inspection requirements. And what is required is to check the wood structural panel, make sure that it's constructed as specified on the drawings, the framing members at the panel, adjoining panel edges, and then the nails or staples that are used on the job site. Now, for checking the wood structural panel, here's some examples that show you from APA and TICO the grade. You would check the grade and the thickness. Now, for here, this shows the structural rated sheathing, structural 1 grade. This is rated sheathing, et cetera, et cetera. And for the thickness, it's shown here. Thickness is 0.451. Similarly here. And here it's 15/32. We have different exposures. We have exposure 1 or exterior exposure, exterior category. Exterior is for those cases where it's going to be exposed to the environment during its end use of the framing, whereas exposure 1 is for those cases it's going to be out under construction. It will be exposed to the environment, but it will eventually be covered up. For pre-framed roof panels, typically you would see 4x8s being used, and we have the 2x6 or 2x4 sub-purlins that are used to stiffen up, and the strength axis of those 4x8 panels are going to be spanning parallel to the sub-purlins, which is something that's sort of unique to the panelized roof systems, and that's why it's very important to have these stiffeners. If you have something greater that are specified 8x8s or larger wood structural panels, then the strength axis is going to be perpendicular to those sub-purlins. Now, for checking one of the special inspection requirements is to check the framing member at adjoining panel edges for high-load diaphragms. Well, as I mentioned previously, high-load diaphragms use 3 by or 4 by framing members. And also, the depth of the framing member is actually 3 by minimum. Because of the multiple rows of nails and the concentration of nails, we want to make sure that we have the adequate framing member there so that we can avoid splitting of that wood framing member. And then the last thing to check of special inspection checks is the nails that are specified. Now, I know in the olden days we used to say, or older engineers used to say, or I shouldn't say that anyway, the 8 penny nails or 10 penny nails really doesn't cut it, because in this example for this slide, 10 penny nails could be any of these nails that you see here. So there could be multiple types of nails out there by just specifying 10 penny nails. Rather than just specifying penny nails, we would specify, either for nails or staples, we would specify the penny weight, the diameter of the head and the shank, the length, and also you have to check the number of fasteners in a row and the spacing of the fasteners in each line. And to get more information on the nails, we have a handy table, table A1, that provides information on standard common, box, and sinker nails to give you that information. We also have details that are in the wind and seismic provisions that shows you the actual spacing of the nails and the staggering of the nails. And some engineers actually include this on the drawings, because when you say staggered nails, or rows of nails. Sometimes it may be confusing, and just a picture is worth 1,000 words, as they say. So it's handy to have these actual diagrams on your drawings. So I think we're going to skip this last poll question.
Yep.
And as I mentioned in the beginning of the presentation, we're not going to get to the FAQs. That's there for your information only. But I want to go over just quickly the resources that are available. APA has really good publication on diaphragms and shear walls that includes design examples, including the panelized roof system. There's a textbook that's available also that's shown here. And if you're dealing with irregular shaped structures, Terry Malone with Woodworks, the Senior Technical Director for Woodworks, has a really good recorded webinar that he's done on irregular shaped structures and diaphragms. We have articles. And the one thing that I want to also point out, which was not included in the handout, is for designing large diaphragms. We have DES 430, and it's an e-course, which I believe Suzanne is providing you the link to. You can watch this for free and goes into detail for designing this type of large diaphragm.
All right, thanks. First, thanks, Michelle and Buddy. That was very informative. We have had a lot of questions come in, so I'm going to jump right in. Buddy, this first one's for you, and I see you've got the page ready. So there was a question on why the 2x4 strut was required if the compression load is going directly into the wood structural panels. I think it was on page 30, 38 maybe. Yeah, that one. And you may still be muted, Buddy.
Yeah, I think you're muted.
Thank you. I was trying to find my button there. Sorry about that. So bottom of page 38, there was a question about why do we need these compression struts or rat runs if the load's going into the panel. Well, really what we're doing here is bracing this gable end truss and making sure that we can get the loads transferred from this gable end truss into that ceiling diaphragm, which is probably going to be framed into the top of the wall there. So we're trying to avoid a hinge from forming here at this location, either when blowing onto the wall and pushing in compression, or as I mentioned, the wall in a leeward direction, sucking and trying to pull this wall out and creating that hinge along the gable end truss in the top of the wall. The other thing that I wanted to clarify, since I'm on this page, we have sharp participants in every one of our seminars. I kept saying a 13-foot end wall stud. It's actually 12. It's a 12-foot end wall stud under that vaulted ceiling. And then the reason I kept saying 13 is because the adjustment factor is that H plus 1 over 10. So you see the H plus 1 over 10 here means we take that 12.1 plus a foot, that gives us 13.1 over 10, that gives us that 30% increase. Good catch for whoever that was that picked up on that during the presentation. Next question, Lori, go ahead.
All right. We had some questions regarding WFCM design, and I think you may have mentioned this, but I'm sure it bears repeating. Does the WFCM have any provisions for LRFD, or is it an ASD only document?
ASD only, and all of the calculations are based on ASD. We convert the wind loads to ASD, or wind and seismic loads to ASD, and then we convert all the resistance factors, or resistance values, I mean, from the wind and seismic standard, we divide by 2 and convert those all to ASD as well.
Great. This one is for you and Michelle. Maybe Michelle would want to take a stab at this one first because she talked about this more. When we talked about drift calculations, when exactly do we need to calculate drift?
Yes, I'll go ahead and take a stab at it, and I'm sure Buddy will have something to add. But for the drift, we need to, or we're required to check the drift for seismic design of non-residential construction if we're designing per the IBC. And then also for multifamily, also designing per the IBC, we would need to check drift for seismic.
Yeah, and I think that pretty much covers it. No for wind, yes for seismic non-res.
Excellent. We have a question come in regarding modeling diaphragms as either semi-rigid, flexible. Are there ways that we can use either, it probably would be, spoiler alert, can we use SPDWS to model a semi-rigid diaphragm?
I'll go ahead and take that.
Yep.
Yes, and actually one of the FAQs kind of alludes to this in the notes. And one, let me back up a second, related to ASCE 7 requirements. There's prescriptive requirements or to say whether or not you are a flexible diaphragm, and then there's a calculated method of determining whether or not it's a flexible diaphragm, which Buddy is showing right there. And if you do not meet those requirements and you do not meet the prescriptive requirements of rigid diaphragm, then one would do an envelope solution, or could do an envelope solution, and say and it would be categorized as a semi-rigid diaphragm. Now, in the wind and seismic provisions, this was a change in the 2000 from the 2008 to the 2015. It now allows for a envelope solution to meet that semi-rigid requirement.
All right. Well, I think that's all the questions we're going to have time for today. I want to thank everybody once again for your spending some time with us. Thanks, Michelle and Buddy, and all of our support staff for another great presentation today. And we look forward to seeing you all again next month.